Hello again.
My name is Enter, and in today's video I will tell you everything you need to know about running your computer vision models on NPU devices. What NPU devices you can choose, how you can optimize your models, what will be the problems with different architectures and different NPU devices. So it's half of an hour lecture, but I hope it will answer all your questions about NPUs and the process of running your models. So let's start. In general, what is the difference between CPU, GPU, and NPU? Of course, the difference is within silicon architecture. So for CPU, it's just one big computational model. Probably it can, of course, be like not one, but 8 streams, or it can be even 32, but in general it's limited amount within same memory. For GPU, the main difference that you have a lot of computational units on your silicon, but the memory access, usually you have some part of memory with fast access, but usually most of memory with slow access, and of course you need to spend some time to synchronization and stuff like this. But in general, like CPU and GPU allow you to run tuning complete tasks, but for NPU it's completely different. On NPU you can't just run some logic program. NPU is completely optimized to run your neural network, like to perform some matrix multiplication super fast and super optimal. Because of this, usually a lot of memory integrated on your silicon near your computational models. And of course, you just run this NPU, usually a single device that perform inference for your main part of your neural network. The purpose of NPU, usually it's not about speed up your calculation. Of course, sometimes it happens for some platforms I had on my channel, for example, like some LackFox boards, some Milk 5 boards. It speed up your calculation a lot in comparison with target CPU. But in general, for a lot of platforms, purpose of NPU is just offload the main calculator like CPU or GPU, optimize power consumption, reduce device cost, and stuff like this. But NPU will complicate all your work. You need to choose your neural network more carefully. It's harder to export your neural network, of course. And of course, you need to maintain pretty complex infrastructure. For example, your CI/CD pipeline will be much more complex because you need to test your code on specific device that will be connected to your CI/CD pipeline and stuff like this. Usually there are no good emulators for a lot of different NPU architectures and platforms. And of course, because of this, you can use NPU chip, but your development will be more expensive. The device probably will be cheaper, and power consumption will be lower. It's usually the answer. When I speak NPU, in general, there are a lot of different names for such chips. Here, just a few of them. And of course, there are a lot of different names. Sometimes it's some of these names specifically for some architectures. Some of them like more general, some of them like more accelerator than computational chip. But in general, it's just a lot of different names under the same hood. And of course, the difference between different NPU models is within architecture that the vendor print on the silicon. And architecture can be completely different, and even if different vendors name same chip like NPU, they can have completely different architecture, and this name doesn't affect a lot. And architecture is the main crucial point for such chips. And of course, this architecture can be targeted for some specific neural networks, like transformer-based neural network or computer vision-based neural network or some other neural networks. And because of this, we can't like just figure some general approach within like architecture and stuff like this. Here is the list of few vendors, because there are much more of such vendors nowadays on the market. By the green, I marked vendors with NPU that I worked with, so I have some experience with them. I know how to set up like CI/CD pipeline for them. I know how to optimize neural network. With orange color, I marked chip that I tested on my channel, so there are a lot of info on my channel about them. But of course, there are much more different neural net NPU chips, a lot more architectures and stuff like this, and they all like complete different. They require you complete different approach to optimize your neural network and stuff like this. But in general, just a few vendors to understand how big and complex this market is nowadays. And of course, NPU doesn't correlate with CPU and GPU. There are some boards where it's integrated in same silicon chip, but for example, like for Hailo, Axelera, or SimAI, it's just M2 board that connected to your already existing board that will perform all calculation. And of course, like for some boards, it can be like GPU model. For some boards, it can be only CPU model. And because of this, and for example, like for VeriSilicon, they provide all the architectures, but it up to you what you will print specifically on your board. So it's also super complicated landscape that different for different vendors and different for different boards. The other interesting question is frameworks. When we speak about NPU, there will be no single framework that allow you to run your neural network on. Of course, there are like TensorFlow Lite, but a lot of vendors, for example, like RockChip, or Hailo, they doesn't support TensorFlow Lite inference on like direct TensorFlow Lite inference on the board. Sometimes you can export like TensorFlow Lite model on your specific board, but it's not possible to run the inference with TensorFlow Lite. For ONNX runtime, it's only few NPUs that are supported. And of course, it's the same for MNN, for Tengin, and usual approach, like each vendors propose its own custom framework to work with their boards. And usually such frameworks works much faster, even in case if this vendor support TensorFlow Lite. For example, 5 years ago, we had an experience with Qualcomm, and for Qualcomm, direct inference with SnapDragon framework was 3 times faster than inference with TensorFlow Lite framework. And it's like regular problem that general frameworks, they usually don't support the boards good. So, and of course, like the problem with such frameworks that different frameworks give you different speed. For example, there are some examples when you can run your neural network with a few different frameworks on the same board, but it will give you different speed. Of course, like different frameworks will allow you to support different amount of layers. And of course, for some frameworks, you can run them only through C++. For some other frameworks, only from C++ and from Python. Okay, here is like there are a lot of frameworks. Here are like there's a lot of vendors, a lot of frameworks, a lot of boards. What is the common between all of this different stuff? And in my opinion, the first common is ideology that's lie behind all this complexity. And ideology is usually about how you can use all these frameworks, how you can use all these approaches, and what like general ideas behind this. And of course, like the first most general idea is how your inference work. And to run your inference, you need to export your neural network. And here is most of approaches, most of NPU boards are usually more or less similar. You train your model, you patch layers of your specific neural network to make them compatible with specific your NPU architecture. It can be a big list of such patches. We will speak about them a little bit late. After that, you upload your model in some intermediate format that works good for specific vendor. Usually it's ONNX, TouchScript, or TF-Lite, but some vendors, they can already work with direct PyTorch models. Some vendors work with some Cafe or MXNet models. After that, you export your model to on your host machine in the format that your NPU understand. And after that, you put this model on your target board and inference it. So it's like the general approach, but of course, if you have some classic framework and this framework can run directly on the device, like ONNX runtime, TF-Lite, PyTorch, and so on, you just skip all last steps in previous logic. And of course, it's a little bit different for some microcontrollers where you need sometimes to export your model directly or write your inference like in code for your specific model. Here is like how this classic approach look like. You train your model, you prepare your model to make it compatible with your NPU chip, you export your model. Usually like for 80% of NPU chip, quantization is required. And this quantization can be actually on different levels. It can be quantization aware training during your training. It can be some post-process quantization where you quantize it with some big data, big list of data before you prepare your model. Or it can be like some direct quantization on the device during the run, or already after you export your model for some framework, you quantize it just in this moment. But of course, there are like 20% of boards that allow you FP16, for example, and for them you don't need this quantization at all. I want to go through few different examples just to make sure that you understand how it will look like for specific platforms. If you want to know more about such platforms, I have videos on my channel. So just go on such videos and look in details about all these platforms. So RockChip. For RockChip, there are few problems. There are no ready-made Docker containers, so you need to set up a lot of different infrastructure. One of them to train, second to prepare model to the format that expert software will understand. Sometimes you can merge these two steps in one. After that, you need to export your models through RKNN toolkit installed on your host device, and after that you just put your model on your device and you can run. what is going on during this expert part, this initial part? You change some specific blocks to make your performance better. For example, you just change output of your models. You cut all post-processing within the model, for example, non-maximum suppression. We will speak about this a little bit later. You switch ReLU activation instead of CLU, but to do this you need to retrain this model, but in general you can go like both approach. With CLU activation it will be like a little bit slower, but the accuracy will be probably just a bit better. But with ReLU you need to retrain your model. And of course, like after you will do all this stuff, you need to rewrite your post-processing for your model to make sure that it will be runnable. And for example, for Hailo board, also there is some specifics video on my channel about this. You need to export your model not to export, you need to prepare your model in PyTorch, for example, some additional layers. After that, you need to export your model in ONNX. You can do this both with like PyTorch, with Cafe, for example. For TensorFlow, they support direct inference, so it's not totally correct about the export here. You just can modify your PyTorch model. After that, you need to export your model to HAR format, which is internal model format for Hailo. After that, you need to modify your inputs and outputs to make it compatible with specific device. After this, you need to perform calibration, and it's most tricky part for the Hailo. And after that, you need to do compilation in specific Hailo format that when already pre-built model will be sent to the device and optimally like projected on the geometry of silicon. So, and only after that you can run your model on the device. But some of these steps, they look pretty like pretty close one to each other, and in general, for example, like export model to HAR, it's just one Python function. Compilation is just different Python function, but you need to control a lot of parameters during all these processes, and a lot can go wrong during that. And for example, like an example with ESP32, and the main trick with ESP32 that there are 5 different ways to run your models for them. And in general, ESP32, it's not like completely NPU chip. It's just some board that can run neural networks on it, but just to show that it can be a lot of different ways. Specifically for ESP32, you can run your models with 5 different ways, and for each one of them, the process will be completely different. I don't want to go deeper right now, just want to mention this. Okay, as I already mentioned, there are a lot of problems with different layers, with different ideas during your inference, and the main problem, of course, is NMS, because all the logics that performed inside of the model, you just can't run this on NPU chip. Probably on some specific NPU you can, but in general, no, it's just performed on some CPU or GPU. So you need to cut this part. Usually you need to cut this part from your model and run it separately. But some vendors, they allow like some internal fallback on their own CPU or GPU and perform all this NMS logic. For example, like in Jetson 30 or in Intel OpenVINA, you will not even think about this NMS process, because if there is layer, like correctly installed layer in your model, everything works perfectly and work nice. There are few vendors with fallback on CPU for such a layer. I never tried them, so it can be like it's STM32, Axelera, and some other. I never tried this specific approach, but I think that it's the same with Jetson and OpenVINA. And of course, a lot of vendors, they doesn't give you support for your NMS, and you need just cut this and write your own code or take some code from vendors where they show some example with this, and rewrite all this part on C++ or Python, of course. Okay. The second problem, like the big general problem, is the memory size. And of course, when you put your inference directly on the silicon, you will be limited by the properties of the silicon chip. And of course, if you just put, for example, 100 megabytes for your model, it will be not possible to run bigger model there. And the limitation can be in any part. For example, limited amount of convolutional block, like limited size of convolutional block, limited size of like distance between different convolution blocks, for example. So here is just a list of some problems that can be specified, like with memory size, and it's usually you find this when you start to export your model. For example, you take your model, start export process. It's look like the model successfully exported, but it doesn't run on your specific device. And a lot of times it's because like it's too big model or some operation are too big. For example, for Hailo, it was average pooling, like it was big operation. For RockChip, sometimes it's like the size of the matrix multiplication. And for different boards, it can be like different questions and different troubles with them. The next issue, it's not like the big problem, but the issue is preprocessing. And for some vendors, you need to put your preprocessing directly on your device. For some vendors, it's separate processor that's like perform, for example, decoding of your videos and direct like normalization of them. And this preprocessing part, it's like, in general, it doesn't look like it's a big part of your model. But when you need performance like 100 frames per second or something like this, you need to start thinking about all this preprocessing. You need to make sure that it doesn't run on your CPU, that some accelerator or GPU like helping you with all this normalization, with all this decoding and stuff like this. And of course, like preprocessing is another question. Some vendors of NPU gives you additional ability to perform this preprocessing on the same NPU. But for some vendors, you need to do this separately or use other possibilities of your hardware device. The next question is transformer models. And transformer models, it's a completely different architecture from convolutional neural networks. And because of this, a lot of vendors, they doesn't support them completely or support just partially. And because of this, you just need to, if you want to run your transformer on your NPU device, you need to do a lot of tests about specifically your transformer model. And because of this, you just need to check each your step. For example, like Whisper model will be not available on Hailo device. but for RockChip, you can't just run regular Whisper model. You need take specific repo with Whisper model and prepare the model somehow, and only after that you can run your model on the RockChip NPU. And transformers is a big pain, and if you have them in your architecture, you need first to think, do I need to keep them? Maybe I can just take different convolutional models that will run same time, and it's a big question. Of course, and we return to the problem with layers. Here is just a list of layers that supported by different platforms from their official documentation. But when you look on this number, you need to understand that it's super tricky numbers. For example, for some platforms, the amount of layers, they can append additional layer, but instead it's not just single layer, it's just merge of two different layers, and these two different layers, they can just allow, they just merge in single layer, and the vendor named it as additional layer. So for some vendors, like half of layers, it can be some merge layers. And of course, when we speak about all these layers, there can be limited support of such layers. And for example, limited size of this layer, limited amount of convolution. For example, here is like the list of supported convolutions for one of the platform. And as you can see, you can't just take random convolution and run it on your device. You need to stay within some regular approaches. Otherwise, you need to fall back this layer or something like this. It's pretty tricky part, because of course, like if you take regular YOLO v5 model, everything will be okay. But if you have your specific model for your specific task that gives you additional accuracy or can, for example, run super fast, probably it will not run on your NPU. And of course, we need to mention like one of the main problem of NPU boards is quantization. And when we speak about quantization, everything is super complex because of course you can just quantize your model before you send it to your device, but for example, Hailo doesn't support quantized PyTorch model, and there are just a few vendors that support quantized PyTorch models, because no one supports quantized PyTorch layers, only like regular layers. Some vendors propose to fine-tune model in their environment, but to do this you need to build your training stack, especially if it's like some complex model. Why you need to do this? Because a lot of models, in my opinion, it's like 30%, they doesn't survive through quantization at all, and around like 20% doesn't survive through quantization well. So a lot of vendors, they gives you a lot of tools that allow you to make this quantization process looks nice. And all these tools, they can, for example, here is like the list of such tools. You can Google about these algorithms, and they give you ability like to increase your accuracy for quantized models. Sometimes they can fix unworking models, but in general, quantization it just doesn't work every time. And when you work with specific platform, you need to understand, do you need to perform quantization here? And if you need, how you should do this? What your model, how it's quantizable, all stuff like this. But of course, for some platform, like for example, like on TensorRT, you just can run your FP16 model, but probably you will just run this on your GPU instead of NPU model. For some, like RockChips, you can run FP16 model, but it will be like 4 times slower than Int8 model. And all this stuff about quantization, it's super tricky, it's super dependent on your specific model. It's even depend on your training dataset, because sometimes same model trained on 2 different dataset, one will be quantizable and one not. So you need to spend time to test everything, to verify this, and to make a decision about all this quantization stuff. When we speak about benchmarks, we need to mention this. We need to understand that benchmarks, they are usually not about real world. There are a lot of, like, millions of tricks that allow you to overcome all these benchmarks, and all the numbers that you saw on different NPUs, like 1 tops, 4 tops, like 15 tops, it's just some random numbers. Yes, they usually say you something about like level of like magnitude of order, about if one platform 10 times more performance than different one. Probably it's at least like 2 times more performance, has 2 times performance. But in general, don't believe all this benchmark, test it yourself. And of course, it's okay if your benchmarked device works like 10 times slower than it was promised by the vendor. Here is like a list. The first table is list of my experiment for different tables. The second one is just official documentation from Jetson, from Nvidia. But of course, like for Jetson, usually they doesn't calculate this with non-maximum suppression part. It's just the regular inference. And as you can see, why I put all these tables here? It's because a few interesting parts. For example, like you can see that the difference in speed for some NPU, it can be completely different for different models. For example, MobileNet on Coral can run within like 3 milliseconds, and YOLO V5S on the same Coral, it's 200 milliseconds. But for example, when we look on some, I don't know, Hailo, the MobileNet will have same speed, like if you run it with batch size 1. But for YOLO V5, it's 20 milliseconds. It's the first tricky question that we will speak a little bit later. So just note this, please. Also, as I mentioned, like difference is in FP16 versus Int8 speed. And also about benchmarks, there are 2 good sites with benchmark of different platforms, but it's super general, and there are a lot of problems with both of these sites. So for example, for RockChip board, all the metrics are incorrect because they doesn't run on NPU. So it's just to make sense about some of platforms with especially with TensorFlow Lite support, you just can go there and look everything there. So and here we go the first issue that I showed with this speed graphics. Why it's so slow? How does the memory work? And in general, this memory issue is completely different for different chips, for different vendors, and for all different stuff. So, for example, for GPU, it can be like some shared memory with CPU. For example, on Jetson, it look like here. But for GPU on your PC, usually the architecture it's like here. And because of this, like memory copy from here to here, it's a long process. And for example, here it's much faster, but there are like some platforms where it can be the same cache for CPU and NPU board. And for example, like for Google Coral, when you see that small model runs super fast, it's of course the first question is because we don't need to transfer a lot of data. We already prepared everything, and all data within usually within the same registers. So and for different vendors, everything will be completely different. And of course, you need just to verify that all your models, you need to check specific models on specific architecture and check like how much memory do you use, how do you send it, and do you use some additional buses. For example, like M2 bus can make your connection super slow for small model especially, and USB bus can make it pretty slow. But of course, the best approach if you have like shared low level memory between your CPU and NPU models. And here is like, for example, how memory works for the Hailo. And as you can see, all the memory just lie within the nearest computational model on the chip. So when your model already there and when your data already there, everything is super fast, but all this transferred process can be a little bit slower to prepare your chip and to prepare it for run your model. And of course, like I already mentioned, NPU, it's not like Turing complete processor, so you need CPU, and in a lot of application, you will be limited by your CPU. So you need to prepare your CPU will be used to transfer your images to NPU, decode your images probably if you receive them and you don't have some coprocessor to decode these images. You need this CPU to image preprocessing, you need this CPU to some additional bus management. And of course, for example, like for some boards, like for RockChip, CPU will be used directly for inference your models, like to split all the data and send it to NPU layer by layer. And of course, like for some models, CPU will be utilized to run fallback layers when your layers doesn't supported by your NPU and you need to fall back it on your CPU. So because of this, CPU is a crucial point in almost in all of your platforms, probably except like Jetson's platforms. And you need to verify how much this computational power you will use for specific your case. And of course, like I already mentioned, this fallback of unsupported layers, it can be completely different. It can be fallbacked on your GPU. For example, Nvidia does this. For example, you can compile RockChip with this support, as far as I understand. And it's because of this, there will be different speed of running your models, and there will be different speed of inference and all this stuff. What other topic I want to cover here? I want to say a few words about C++ and Python. Of course, like 99% of researchers nowadays, they train their models in Python. Usually for 99% of platforms, you need Python to export your model to your inference engine. But for inference, Python is not the most popular solution. For a lot of boards, you can inference only on C++. Like 99% of boards, I think even 100% of them, they support native C++ inference. But when we speak about Python inference, just a few boards can run Python on them. And the smaller your board, the closer to microcontroller, the less probability that there will be Python support. So you need to remember this when you're choosing how to choose your NPU, how to run your models. I didn't mention anything about training on NPU, and it's completely different story, but there is completely different class of processor, of NPU processor to do this, and completely different logic behind them. But just to mention that it exists, and sometimes you can run your NPU models on such devices, I did this slide. And that's all. You can subscribe on me on a lot of different platforms. Usually I speak a lot about computer vision, about different NPU devices, and some 3D cameras, for example. Thank you for watching. Goodbye.